This is the periodic table I use in all of my classes. I've been using it for many, many years from Dr. Winter's WebElements.com website. So since all my work is standardized on this, if you use a different periodic table, you'll have slightly different numbers. The numbers that I want right now are the atomic weights. So I want the 1.008. There are a number of different interpretations of that 1.008. What all the interpretations share, however, is that that's an average weight. You take into account all the naturally occurring isotopes of hydrogen. You figure out the atomic mass of all those isotopes. You figure out their percent abundance, and you put it together, similar to how your grade is probably calculated, a weighted average. And you put it together and you get the 1.008. But as far as units, I'm not going to use the Unified Atomic Mass Unit, AMU or U. That's because, not that there's anything wrong with that, it's just that's for individual particles. And that's not what we're dealing with right now. We're dealing with large quantities of a substance. You're weighing things out on the balance. You're scooping things into the balance. So we need a way to connect the macroscopic world to the microscopic world. So the interpretation I'm using is molar mass, the mass of 1 mole. So if you take 1 mole of hydrogen, the mass on average is 1.008 grams. That's the way you should think of it when you're doing calculations, because that will help you keep the unit straight. This is the way it's usually reported. In everything else that I do, if you see this italicized capital M, that refers to molar mass. But you can only use that if you're printing out, typing up documents. Because if you don't italicize it, it means something else. M is horribly overused in chemistry. And italicized M means molar mass. Non-italicized capital M means something else. Lowercase means something else. There are numerous interpretations of it. So if you're having to write it out, just write molar mass. Don't call this molecular weight, because hydrogen is not a molecule. And so molecular weight can only be used with molecules. It can't be used with elements. It can't be used with ionic compounds. That's another reason why I just use the term molar mass. It stays away from all of those problems. Let's start with water. You look at the chemical formula, it's H2O. There are 2 hydrogens. There's an oxygen. Then when you report it, you look at the decimal places for both. They both go to 3 decimal places. And so I write my molar mass to 3 decimal places. I'm not going to write it as 18. I'm not going to write it as 18.0 or 18.02. It's 18.015 because the periodic table I use goes to 3 decimal places. And just one last reminder on this. This is the way to think about it when you're doing a calculation. This is the chemical formula for glycerol. So we look at all the elements in there. How many carbons are there? There are 3. How many hydrogens are in there? Well, there's 8. I just counted all 8. Because that 3 on the far right affects everything in the parentheses. So there's 3 O's, 3 H's. There's an additional 5 H's because of the C3H5. And as I mentioned, there are 3 oxygens. All 3 of those atomic weights go out to 3 decimal places. So that's how I'm writing the molar mass, 3 decimal places. Now we'll do sodium chloride. Well, 1 sodium, 1 chlorine. And when you write it, I'm choosing to write it to 2 decimal places because the chlorine goes to 2 decimal places, even though sodium goes to 3. Now, this is something that's instructor specific, but if you're asked for the molar mass of sodium chloride, this is the molar mass. And that's because chlorine doesn't go out to 3, there's too much uncertainty. But it's rare to be asked a question that simply says, what's the molar mass of this? Usually, the reason why you're calculating molar mass is to do a calculation with it. So, you can write this to all the decimal places. You just have to remember that even though I wrote it to 3 decimal places, it's really only good to 2, which means 4 significant figures when you do a more advanced calculation using the molar mass. It's very unlikely that the molar mass will dictate the significant figures of a calculation, however. Now, this is an example of a hydrate. The name of it is calcium chloride dihydrate. And I'm doing this one for 2 reasons. One of them, I want you to see how to calculate the molar mass of a hydrate. What the heck does that dot mean? And another reason is, look at calcium. Look at the atomic weight of calcium, 40.078, and there's a 4 in parentheses. Well, if you look at that Webb Elements periodic table, there's a footnote at the bottom. And if there are no numbers in parentheses for the atomic weight, the uncertainty is assumed to be plus or minus 1 in the last decimal place. However, the uncertainty for calcium is actually plus or minus 4 in the last decimal place. So what does that mean for you? Well, for my classes, nothing. Just, if you've got a number in parentheses like that, just throw it away, ignore it, because we're not using those uncertainties. We've got 40.078, that's calcium. We have 2 chlorines. Now the dot 2H2O, that's not multiplication. That means it's a hydrate and you have 2 water molecules associated with each calcium chloride. Well, that means you have 4 hydrogens and 2 oxygens. And when I add them up, I go to 2 decimal places because of the chlorine. But like before, if you're using this in a calculation, you can keep all the decimal places. This is lead-2 acetate, which is also known as sugar of lead, which admittedly gives me the creeps when I think of it that way. If you go back to early Roman times and before, they used to make something called sapa, which was a sweetener. Now, you didn't have a whole lot of options to sweeten things back then. They would take grape juice and put it in metal cookware and reduce it over heat, and as the water evaporated out, it would get thick and syrupy. And it was sweet, so you could add it to things as a sweetener. Not like you had a whole lot of choices for sweeteners, so it worked well. If this was done in lead-based cookware, it would cause the lead to leach out into the sapa and be extraordinarily high lead content in that sweetener. There is some debate over how much that was actually done and how much of a problem that was, because from what little I've read on this, the metal cookware at that time was mainly copper-based. And that's not a problem with copper-based because you don't have lead in it. Anyway, it's a potential problem. Well, what's the molar mass of this compound? Well, you find lead, and then we've got 2 of everything in parentheses. 4 carbons, 6 hydrogens, 4 oxygens. I'm going to round that to 1 decimal place because of the lead. But just as before, you can keep all the decimal places if you're going to use this in a later calculation.